I thought I'd start off today with a little review. In the last lecture, there were an awful lot of new terms and words that were thrown out. And I don't know about you, but when I see things like that for the first time, I have a very difficult time remembering those things. So especially if there's some relationship between one and the other. So I thought it would be worth our time here to spend, just go back and review a few of the things we've already talked about. So let's go all the way back. Let's go back to the original picture we had of the structure of the Earth that was created from the protoplanet. The structure of the Earth, of course, threefold. You have the core. Now, the core is basically made of iron, molten iron. Well, actually, it's probably iron and nickel, but basically iron. Remember now, that's the most abundant metal in the universe. It's molten, except for perhaps the very center of it. There's still an argument as to whether the center might be solid, or perhaps if it's not solid, a very, very viscous liquid. But the core is made of the iron, and the average density is supposed to be about 15. Then surrounding the core now, we have the great mass of Earth, which is called the mantle. The mantle is made up of a rock called peridotite. Peridotite is an iron-rich rock, not as iron-rich, of course, as the core, but it has enough iron in it that the average density of the mantle is about 6. So note 6 floats on 15. And that's an important concept to get across, is that at this scale, we're talking density separation and floating on each other. So the mantle literally floats on the core. Now, some people think the very bottom of the mantle could actually be a mixture of oxides again. In other words, down there, the temperatures and pressures are so high that maybe even the peridotite decomposes into its respective oxides, aluminum oxide, silicon oxide, iron oxide. That's a theory, but I'm not sure whether it's true or not. Then finally, on the very outside, we have that outermost brittle layer that we call the crust. The crust, now averaging about 40 miles thick, is made up of two components. We have the oceanic crust, which is made up of basalt, and then we have the continental crust, which is made up of granitic rocks. Now, I say granitic rather than think granite itself, because the fact of the matter is there are two rock types. There's granite, which you all know, or heard about at least, and then there's another called granodiorite. Actually, not many people can tell them apart, and so they look very much similar, so we just sort of group them all together and simply call them granitic rocks. So that's basically what the continents are made of. Well, anyway, that is what the picture was for a long, long, long time until we came up onto plate tectonics. Now, just beforehand, we had a discovery made by the seismologist that said that, well, the structure isn't quite as simple as that, as mantle crust. They said they had discovered down below the surface this layer from about 100 miles down to about 250 miles down that was special. It was different from the rocks above and below in that these rocks were plastic. Now, what plastic means, remember, it's a solid, there's no doubt, these are rocks, but they act like liquids. Now, what liquids do that solid rocks don't is they flow. So here's that layer now where we're going to talk about in a moment where all the convection cells are. So that's the asthenosphere. Now, above the asthenosphere to the surface is a layer that they call the lithosphere. Now, the lithosphere is brittle, and it means what it says. When you do something to it, it's going to break. But remember now, this is important, that the lithosphere is not just the crust. The lithosphere is composed of the crust plus the outermost portion of the mantle. So it's actually a combination of mantle and crust that makes up the outer portion of this lithosphere. Well, back to the asthenosphere now. The asthenosphere is the place where all these convection cells are. This is supposedly the source of the energy and the mechanism we're going to use to break the lithosphere apart. Now, I think it's important to really understand these convection cells. Now, I'm sure you know what a convection cell is, but I want to go sort of through this thing of convection cells just to make a point, or several points actually. So let's talk about convection cells. The simplest example I can think of, you put a pot on a burner on a stove. You take a beaker of water and you put it on a Bunsen burner, and it heats up the water. As the water heats, of course, it expands, density goes down, rises to the top of the pot or the beaker, flows out of the top, cools, density goes back up again, becomes heavier, and it goes back down the sides to be reheated. So basically that's a convection cell. And any watching of a boiled pot of water, that you see the convection cells. But now what I want you to do is consider something a little bit different. What I want you to do now is consider a fish poacher. Now, I don't know if you know what a fish poacher is, but it's a pot. It's about that long, it's about that wide, maybe that deep, and it's designed so you put a whole fish inside it to poach it. Now, see, I know all this stuff because I do all the cooking in my family. But anyway, that's what a fish poacher is. Now, it's too long to put over top of one burner, so usually you put it over top of two burners. So the picture now is a fish poacher with the water heating up, but you got two sources of heat now. Over each source of heat, you have a convection cell rising to the surface, going out on the surface, cooling and back down. But note you have a convection cell over each heat source. And now this is very important too. Note within this convection cell system, you have a rising portion of convection cell and then a downgoing portion of convection cell. Rising portion of a convection cell. In other words, they alternate like that, rising, sinking, right? You never have two rising portions together. That's impossible. Nor do you have two sinking portions together. They always alternate like that. And that's sort of an important point to be made, I think. Now, here's the next thing I want you to do. I want you to picture taking a slab of wood and cutting it to fit the inside now of this fish poacher and put it down on the water. Now, obviously, it floats. Why? The density of the wood is about 0.5. The density of the water is 1. Light things float on dense things. So here's this piece of wood now floating on this water in its fish poacher with these convection cells coming up underneath and going back down again. Now picture this now. The water coming up underneath the wood, rising portion, spreading out underneath the wood plank, and it sort of pulls by drag on the wood. Well, that kind of thing like that, that's tensional forces. So above the rising portion of the convection cell, you generate tensional forces within this slab of wood. Where the water is coming together to go back down, you have compressional forces being generated in the slab of wood. So note, they alternate. Tension, compression, tension, compression. You cannot have two tensional zones next to each other, nor can you have two compressional zones. It always alternates. Tension, compression, tension, compression. Now here's all I want you to do. Very, very simple. All I want you to do in your mind is to change that slab of wood to the lithosphere. And I want you to change that pot of water to the asthenosphere. And then I want you to change those two burners on your stove to two heat sources coming up from below, from the center of the earth. Everything else is the same. You have convection cells now within the asthenosphere, rising up underneath the lithosphere, creating tensional and compressional forces within the lithosphere. Now, the lithosphere is brittle. What it means is if you try to do something to it, pull it apart, jam it together, it's going to break. So now we're going to break things, okay? Let's take up the tensional forces first. What we're going to do now, we're going to take the lithosphere and break it. We're going to break it at the tensional forces and at the compressional forces, and we're going to break this thing now into pieces. Remember, the pieces now are going to be called plates. But let's talk about the tension first. We're going to talk about taking a rising portion of a convection cell. We're going to bring it up under the lithosphere, but important now, this lithosphere is a continental lithosphere. In other words, the rising portion of the convection cell is under a continent. So we're talking granitic rocks here in the crust. What's going to happen? Tensional forces are going to be generated within the crust, within the entire lithosphere, and it's going to break. What you're going to see from the very beginning are cracks starting to form from the bottom of the lithosphere, working their way toward the surface. Now, once they get to the surface, then they're going to line up. And so on the surface, what you're going to see is a series of cracks opening up under tension. We call that force, that pulling apart, rifting. So we'll call this a rift zone. And so the rift zone starts to develop. Now, the next thing that's going to happen, back down to the asthenosphere, at the very top of that rising portion of the asthenosphere, right at the top now of the asthenosphere, this layer of rock that was acting like a liquid becomes one. It melts and creates a magma. Now, unfortunately, we don't have time to go into the mechanism by which magmas are formed, so you'll have to take my word for it. But the magma that forms is always basaltic. Now, remember, that's the lowest viscosity of all. It's the one that flows most readily. And so what happens once this magma, this basaltic magma forms, it starts to work its way up through those cracks. Somewhere along the line, once it gets into the continent, it's going to run into water, groundwater, which we'll talk about in another chapter too. But it's going to run into groundwater, and the groundwater is going to become heated, and the groundwater is going to rise to the surface. So along this rift zone now, what you're going to expect to see, you're going to expect to see things like hot springs. Some places the water actually boils. And so out of these cracks comes steam squirting up in the air, and we call those fumaroles, and we'll talk more about those when we get around to talking about volcanoes. And the other thing is, sooner or later, some of this basaltic magma can come to the surface to become basaltic lava and flow out to form lava flows. Now, these are not going to be any great lava flows. This is not going to be like the Columbia Plateau. These are fairly small little lava flows, and maybe even there's enough gas left in the magma when it gets to the surface to blow some of the molten rock up in the air. We call those fire fountains, maybe 1,000 feet, maybe 2,000 feet at the most. And as it blows up in the air, it breaks into little pieces which solidify on the way down, and those little pieces then become what we call cinders. So the cinders accumulate around the point where all this is coming out into what we call a cinder cone. So the point is that this zone now, this rift zone, is volcanically active. What does it mean? Well, what it means is we're talking about a continent starting to break up. Question, can I send you someplace to see a place like that? Yes, I can. I think all you need to do is go to Albuquerque. Coming up out of Mexico, right up through the center of New Mexico, right through the suburbs of Albuquerque, on up through Los Alamos into central Colorado, you have a zone just like that. And you can go there and you can see little lava flows, and you can see hot springs, and you can see cinder cones. I don't think I've ever remembered seeing any more fumaroles there, but you can see the volcanic activity. In other words, it's still going on. Now, question is, does that mean that North America is breaking up? Well, I was on a field trip to the rift last summer, and I talked to the people who were leading the trip, and I asked them, that was their bag, this particular rift zone. It's called the Rio Grande Rift, by the way. The reason why is because the Rio Grande River follows it for a while before it heads down to the Gulf. So I asked them, is it meaning that North America is breaking up? And they seemed to all be of the opinion that it was not. They called it an aborted rift. In other words, the idea is if nature had continued on, yes, it could have split North America up. But apparently this rift started, it developed, and then it sort of died. It's now aborted. Whether it comes back or not, we don't really know. That's something for the future to tell. But the whole point is, when continents break up, that's what they look like. You form the rift zone first. Now, step number 2. Here's all you have to picture. Now, I used to do this when I was teaching the small classes to demonstrate the following. You know those flat party cakes you get, just one layer and on a piece of cardboard? I used to have a bakery make me one and put it on one piece of cardboard, but put it then on another piece of cardboard, budding 2 pieces, and put the cake on top of that. And they never understood why I wanted to do that, but I said, just do it. And so what I did in class, and remember that icing that's on it? It's like glass when it solidifies. I took those 2 pieces of cardboard and started pulling them apart. And the first thing that they saw were the cracks forming in the icing. That's the rift zone, see? So here's your rift zone forming. And now I just want you to visualize this in your mind. As you continue to pull that apart, what happens is the cracks get bigger and bigger, and pretty soon that central part of the cake where the rift zone was starts to collapse on itself and forms a valley in the cake. Well, since it's a rift valley, we call it a rift valley. Okay? So that would be step number 2. Is there some place I can send you for that? Well, yeah, a little further trip, I might add. But if you go to East Africa, there's the East African Rift. It starts up in Ethiopia, extends down to Mozambique, and is pulling apart. Right now, for example, it is active, lots of volcanic activity going on there. And if it continues now, again, the big if, the part to the east will eventually pull off and become a very large island sitting off the east coast of Africa, just like Madagascar is. Now, Madagascar is much smaller, but it formed in exactly the same way. Well, that would be step number 2, the Rift Valley. Then note, sooner or later, one end or the other is going to reach the ocean, and waters are going to start spilling in. Well, as we speak, there's already water flowing into the northern end of the Great Rift Valley of Africa from the Red Sea. And as a result, they're forming these saltwater lakes that are growing in size every day, much to the chagrin of the people who live there, because here this land was once used to raise crops to feed their family or whatever. Now it's underwater. And it's salt water, so they can't even use it. So the idea, if that were to continue, if again, the whole Rift Valley would fill, and now we have what we call a linear ocean. By definition, what a linear ocean is, it's a long arm of the sea, open at one end to the open sea, but still landlocked at the other. And the question is, can I show you a place like that? And yeah, if you're in the Great Rift Valley of Africa, you don't have far to go because that's the Red Sea. The Red Sea is open to the Indian Ocean on one end, still landlocked at the other. That little bit of rock, though, the Suez Canal cuts through, that's all there is. Note, when that breaks, now Africa moves away and becomes a huge island, and we start to have the creation of an ocean. So that's the next step. For example, the thing that characterizes oceans, remember? Oceanic ridges. As we speak, there's an oceanic ridge already forming on the bottom of the Red Sea. And so from then on, it's simply going to be a question of things opening and new oceans being created. Well, that's what happened in Pangaea, you see, when she broke up. Now, while we're on Pangaea, I want to step back for a second and revisit Wegener. Because, see, Wegener had all this figured out, in his own mind at least, and no one would listen to him. Turned out he was right. He never lived to see that, however, because he died in 1930 on an expedition to Greenland. But Wegener, did he have any evidence to prove what he was saying? Yes, he did. The evidence he had in 1915 would be what we would consider today irrefutable evidence that he was right. For example, he matched up from the coastline of South America to the coastline of Africa. Rock types matched up, structures matched up, fossils matched up between the two continents. There was, for example, an amphibian you find in Africa and also in South America. Amphibians don't swim across oceans. There are plants that matched up. There's a plant called, sort of a fern-like thing called Glossopteris. The seed was very, very big. It doesn't blow all the way across the ocean. Birds don't carry it all the way across the ocean. It had to be together when that plate was formed. And the real evidence, glaciation. When all these guys were together now, the whole area of South America and South Africa and also Antarctica and Australia, which were all together at the time, were undergoing glaciation. He matched up between South Africa and South America, glacial deposits, glacial striations. No doubt, if he had presented those data today, we would accept it. They wouldn't accept it then. So anyway, it took a while, but he was finally vindicated. Unfortunately, he was dead at the time. But anyway, here we have now growing oceans. The Atlantic Ocean is opening, the Indian Ocean is opening, and we're creating the Arctic Ocean. So here we have 3 oceans opening. Now, here's the point. You just can't open oceans without doing something else unless you want the world to blow up like a balloon. So the idea is now, if you're going to do that, somewhere, if you're creating new ocean in one place, you've got to get rid of old ocean someplace else. Where could that possibly be? Where is a place where you could possibly see old ocean being consumed? Well, see, that's what Hess came up with. Actually resurrecting an old idea that was presented by Holmes back in 1928, 1930s. Hess in 1960 said, well, it's got to be where those deep sea trenches are. The compressive forces, you see the other half of the coin, the compressive forces start the down bending of the ocean. There's your deep sea trench. And if you continue that, it's going to break. And the oceanic lithosphere now is going to dive down into the mantle and be consumed. For every cubic mile of new ocean lithosphere you're making an oceanic ridge, you've got to consume a cubic mile at one of these zones of subduction, we call that now. So the zones of subduction are where this thing's being consumed. Now, the idea is the ocean that's being consumed, of course, is the Pacific, the once great ocean. The thing about the zones of subduction now. Down in the zone of subduction, there are 2 kinds of magmas that are being created. Granitic magma and andesitic. Now, we haven't mentioned andesitic up until now, but here's the big difference between them. Obviously, they're different in composition, but for us, the difference again is going to be in viscosity. Remember, basaltic magmas have a concentration of silica about 45%, and to sort of give you a picture of what the viscosity would be like, I suggested comparing it to olive oil. Andesitic magmas have a concentration of silica of about 55%, and if I were to pick something to sort of represent its viscosity, I would pick pancake syrup. And then, of course, remember, granitic magmas, 75 to 80% silica, thick and sticky, and the material I picked to sort of compare that would be molasses that you've kept in the fridge for a day. So it's really a big difference between the andesitic and the granitic. So in the pictures now of the zones of subduction, here's what you see. You see the andesitic magmas rising to the surface, creating on the surface a range of volcanic mountains called arc volcanoes. Now, if the zone of subduction is relatively just offshore, let's say within a few miles or perhaps a few tens of miles, then that arc volcano chain is on land, and we call it a continental arc. That would be like the Andes or like our own Cascades. On the other hand, if the zone of subduction is a little bit further off and you're out there maybe 100 miles, maybe 200 miles or so, then the volcanic chain builds, but it builds from the ocean floor, eventually to strike through to the surface and becomes a chain of volcanic islands. The best example I can think of would be the Aleutian Islands, but actually all the way across the northern Pacific and down along the western margin, you have these, basically these island arc chains, and that's the result again of reactions at the zones of subduction. Now, the granitic stuff, it rarely ever gets to the surface. Certainly in these zones of subduction, it doesn't. What happens in the little pictures, the big blobs coming up, that's the granitic magmas. And what it does, it emplaces itself in the edge of the continent. Note, adding granitic rocks to the continent. Now, let's just sort of think about this continent business. A question is often asked, with this subduction business, we always say the oceanic crust lithosphere, the whole lithosphere, subducts beneath the continent. Question was asked me many times, does the continent ever subduct beneath the ocean? The answer is no. It's impossible. Why? It's a density thing. The density of the continent is only about 2.9. The density of that oceanic lithosphere is about 3.1. Light things don't go under heavy things. Heavy things go under light things. So it's always going to be the oceanic lithosphere diving beneath the continental lithosphere. Okay? Now, here's the picture then. We have these opening oceans. We have the Atlantic Ocean opening. We have the Indian Ocean opening. We have the Arctic Ocean opening. These are the new oceans. You're creating new ocean bottom. When did all this start? Well, according to Wegener, 200 million years ago, which means if you were to date the rocks on the ocean bottom of the Atlantic, the Indian, or the Arctic, the oldest crust you would find, the oldest, since that's what we sample, the oldest rocks you would find on the ocean bottom would be about 200 million years. And they are. And where would they be? Well, they would be next to the continents, because as the continents moved away from each other, they take the oldest rocks with them, making new rocks at the oceanic ridge all the time. So if you look at the rocks of the ocean bottoms, the oldest rocks of the ocean bottom is always next to the continent, and they get younger and younger. And at the oceanic ridge, they are literally today old, because they're being made as we speak. Now, how about the Pacific? The Pacific Ocean now is closing. It's being eaten up on 3 out of 4 sides, you see. Here's a question. Does the Pacific Ocean have an oceanic ridge? Is new ocean being created in the Pacific? And the answer is yes. I mean, every ocean has an oceanic ridge. So out there in the Pacific, there is an oceanic ridge. It's creating new ocean bottom. Matter of fact, it's creating ocean bottom about 3 times faster than the Atlantic. But the question is, how can you create ocean bottom new and yet have the ocean closing? Well, it's very simple. I mean, if you eat it up faster than you're making it, then it's going to close. I mean, if somebody's making cookies and throwing them onto the pile, and somebody comes in and starts eating the cookies faster than making the cookies, the pile's going to be gone. So the idea is now that the ocean is closing because it's being consumed faster than any new ocean bottom is being created. Now, one last comment about the ocean rocks in terms of age and the continental rocks. Remember the story now, if we go way back, the whole crust formed for the first time maybe 3.5 to 4 billions of years ago. Question, the crust that you see today, are any of the rocks that formed then still here? Well, yes, there are. The continental rocks, some of the continental rocks are still here. For example, there have been rocks from the continents collected and dated at 4.1 is the oldest, 4.1 down to 3.5 billions of years. So there are some of the original granites still there. Why? They don't subduct. There's no way of getting rid of them. Matter of fact, you're adding new granites to the edge of the continent from the zones of subduction. Why aren't the continents growing in size? Well, we're going to talk about other processes called weathering and erosion that's stripping them away and dumping the stuff into the ocean, you see. So there's a balance there. The total volume of the granitic rocks has remained sort of constant over all time. But the point is, there are still some of the original granitic rocks there from the very first. How about the ocean bottom? How about the oceanic crust, or lithosphere, if you want to look at the whole thing? Is there any of the original still left? The answer is no. None of it's still left. I mean, Of course, all the rocks of the Indian, the Atlantic, and the Arctic, they're only 200 million years old at the most. But back to the Pacific again. In the 3.5 billions of years that have passed, the original rocks of the Pacific Ocean bottom, that original lithosphere, all that has been consumed and replaced by new stuff. For example, the oldest rocks on the Pacific Ocean bottom are just a little bit older than the rocks of the Atlantic. The oldest rocks in the Pacific are only about 250 million years old. So note, all of the ocean bottom rocks are all relatively new compared to the continental rocks. Now, the last thing I'd like to talk about, and this is really sort of neat too, I sort of like this kind of stuff. The question is, will this go on forever, this opening of the Atlantic and the Indian and all that? Well, in other words, picture this now. Will the Americas ever crash into Asia? That's the question I've always asked in class. Well, not if a geologist by the name of J. Tuzo Wilson is right. J. Tuzo Wilson is a Canadian geologist, and he was a big gun in the whole area of plate tectonics when the whole idea was being put together. J. Tuzo Wilson had an idea. He said, what if this stuff, this motion we're talking about, this breaking up, is all part of a gigantic cycle? Which seems reasonable, because everything out there in nature's in cycles. You can just name all kinds of cycles out there. So here's his idea. What his idea was you start off with a supercontinent surrounded by a superocean. Then what happens is that supercontinent breaks up and creates new oceans at the expense of the old ocean, the great ocean. And you create continents which drift away from each other. And all that drifting away business, that goes on for about 250 million years. And then at the end of 250 million years, what happens? It all starts to go back again. Now, they don't all go back at the same time, but by 250 million years, everybody's going back, and it takes another 250 million years to do it, but they all eventually go back and form another supercontinent surrounded by another superocean. Now, the two continents are different, and when they break up again, they're not going to form the same shape or size or number of continents, but that's the idea of his cycle. It's a 500 million year cycle, 500 million years. Question, if he's right, which I have no reason to believe he isn't, if he's right, how many of these cycles could there have been already? Well, if we just assume, and I really don't know when plate tectonics as we know it now really started, but let's say it started maybe 3 billions of years ago. Well, the question is, how many half billions can you have in 3 billions? The answer is 6. So maybe the one we're in right now is the 6th one, you see. Well, here's some interesting questions then. If we look at the present oceans that are, quote, opening, the Atlantic, the Indian, and the Arctic. The Atlantic is definitely opening. There's no doubt about that one. The Atlantic Ocean is opening at about the rate at which your fingernail grows, maybe an inch per year. The Indian Ocean, I think, is about as big as it's going to get. The reason why I say that, the Indian Ocean, of course, opened as Australia went eastward. Of course, then Antarctica went down, but it was Australia going eastward that created the Indian Ocean. But as we speak, Australia now is heading north toward mainland China. Why I know that? There's a zone of subduction between Australia and mainland China. It's the Indonesian zone of subduction. What that tells me is, you see, things are closing up. So already, the Indian Ocean is starting to close, at least in the eastern portion. The Arctic Ocean seems to simply be up there resting. It's not opening, it's not closing, it's sort of waiting to see what everybody else is going to do, I think. But the Atlantic is still opening. Question, will it ever open to the point of the Americas crashing into Asia? Well, all you have to do is figure this out. We're 200 million years into a Wilson cycle. We got 50 million years to go. How far will the Americas travel in 50 million years? Well, let's say even at 2 inches per year, moving westward. All you have to do is figure out how many miles that is in 50 million years at 2 inches per year. It turns out to be something on the order of maybe 800 or 900 miles. So in other words, the furthest west the Americas will ever go is another 800 or 900 miles. Note, that's not even as far as the Hawaiian Islands, you see. So the answer to the question, will the Pacific ever close? The answer is no. Before that'll ever happen, all the continents, including the Americas, will start heading back. And once again, the Pacific, which is our great ocean of the day, will once again become the great ocean of tomorrow around the next supercontinent. And that's the Wilson cycle. And it just goes on and on and on like that. And next time we're going to talk about minerals. Finally, we have to get into talking about the things of which all these rocks and stuff are made. It's important to understand minerals. They're not always the most favorite topic of students, but you have to understand them. If you want to know how rocks are named and how they respond out there to weathering, how the landscape is sculpted, you really have to understand what the rocks are made of. So we'll pick up the next topic, minerals.